Hello everyone, welcome to AI Anytime channel. In this video, we are going to explore a multimodal small language model, MSLM. So it has very good vision capabilities, smaller in size, and you can again use it on a compute limited hardware. Like for example, if you have a single consumer GPU or also on CPUs, you can use this model for inference and building multimodal RAG applications. Now, this video is going to be interesting because I will also cover the mathematical intuition behind the visual encoder that we are going to leverage. Of course, that's going to leverage from this model. The model name is Imp-V1-3B. So Imp version 1 and 3B parameters. So it has 3 billion parameters. So it's a smaller multimodal model that you can call it. Now it has been created from the combination of models. One is of course Phi 2, which is again a small language model, and then it uses a visual encoder called SigLIP. I will talk more about SigLIP because you should understand that why SigLIP is important in the context of this multimodal small language model and why the creators, they would have selected SigLIP, which is based on Sigmoid function. We'll talk about that fantastic visual encoder model, which is around 400 million parameters, 0.4B. So it's a combination of Phi2 and uh, SigLip. So SigLip is by Google, by the way. So we're gonna look at in detail that how SigLip can help you if you are training a small language model or a multimodal language model, or also in the pre-training phase. That how SigLip can contribute. Now you can use this model to build n number of applications. You can use this to you know uh, analyze certain images. You can also help you with the test cases generation from your application screenshot. It can help you analyze medical images, which is not of course internal but external, your different websites and n number of other images to find out anomalies and stuff like that. So we'll do this experimentation in Google Colab. We're going to use the V100 GPU, but you will be able to do with T4 as well. So you can do it in free GPUs of Google Colab as well. I will explain that mathematically and also theoretically that how SigLip has contributed to create this fantastic small multimodal model. So it's like a dynamite. You have a small dynamite that really can help you build RAG applications as well. I'm also right now working on some those kind of capabilities. So let's jump in and see how we can experiment with this multimodal small language model and how we can leverage that for certain use cases. All right, so here you can find out Imp version 1.3b on Hugging Face. You can find out that on the Hugging Face repository here by MillVLZ. It says a very small man can cost a very large shadow, which is, I feel, correct. And it has some introduction that talks about these two models, Phi2, SigLip. I have 3 videos on Phi2, also how to fine tune a Phi2 model. If you are interested, please find those in fine tuning LLMs playlist. Now, this is SigLip, and I want to focus on SigLip. It's a model by Google. You can see fantastic model. So it's a very fancy name though. It's an acronym for Sigmoidal, and you can see it says shape optimized model. Right? So it's a Sigmoid laws for language image pre-training. That's the acronym for this model. And this is a visual encoder. So it encodes the visual. I'll explain that in a very simpler term. So if you are not familiar with these terminologies, you'll be able to understand now. Now, it's a fancy name for a model, that has been taught to recognize how images and text are related to each other. So the text and images mapping gets along, using this visual encoder model of SigLip. Now, imagine if you saw a picture of a pet like dog and then a word dog. So it basically understands that these two things are connected. So it basically finds out the link between and an image and a given text that is relevant to that particular image. Now, and there are a lot of models like that, right? We have alternatives like Clip, for example. You would have heard about Clip if you are working in this field. Now, so what's new about SigLip? Why are we not using Clip in this case? So there's an advanced version of this kind of models that we call it Clip. Now Clip can look at an image and a piece of text and figure out how well they match. Okay, and this is pretty advanced. But SigLIP does the same thing, but I will tell you that how it is different from a clip model. We'll talk about that in detail. I have my tab open here and I will discuss that. Uh, SigLIP learns well, it's really works good on a smaller data if you have less data of your visuals, and I will explain that. And it uses something called Sigmoid law. So let me write it down here and explain that. So I'll just write it here and say, uh, okay, and I'm going to talk about SigLIP here. So let's do that. Now, SigLIP is uses something called sigmoid laws. So let me just write it over here. Now you should focus on sigmoid laws, which is a way to measure how good or bad the model's guesses are without needing to compare every single image text pair at once. So, and this is how sigmoid laws helps you. It's like giving the model a more focused quiz rather than a massive, final exam and stuff like that, right? So making it easier for model to learn from its mistake. Now, we'll go into detail, and because of this sigmoid loss, this new method, SigLip can handle a lot more data at once. So you show it once, and by scaling up to the batch sizes, right? If you go it more technical, it helps you scaling up to the batch size. Even when there is not a lot of data, it still does really a good job, which we will not see that in case of clip. And it's being able to learn effectively in both a huge lecture and a small seminar as well. So if you go a bit layman terms. Now I'll give you some examples of SigLip, what it can do. So the thing it can do is a lot of things, by the way. The first is it can do a image text matching. It can do image text matching. So if you give SigLip a bunch of images and a bunch of captions, it can figure out which caption goes or maps with the which image. So for example, if you there's a photo of a beach and then you give a caption like sandy shore at a sunset, so SigLip can match them correctly. So this is the first thing that it does, image text matching. The other can be the most important thing, and that's why it is critical in this smaller language model, because you are going to create a small model having less parameter, so you will also have less data. So, and that's why this helps to better understand with less data. So that's also a USP of using SigLip, as a visual encoder. So of better understanding with less data. So this is one of the USP of SigLip. Now, if you look at the visual encoder models, if you want to train a better multimodal LLM from scratch, then you need tons of data to learn something well and find out the different varieties of patterns and whatnot. But SigLip is more efficient in its learning process. It can understand relationships better between images and text, even without there is not much as data available to learn from. Now the architecture is important, that what it uses. It uses again vision transformer. We'll talk about that. Now let me draw it here and show you. So if we talk about the architecture, so it uses VIT, so which is vision transformer. It uses VIT 400M. That's the underlying, like the backbone of this model. It's a variant of a structure known as a vision transformer. So we have transformer for all the text-based models that we work. Similarly, we have VIT. If you are not aware, it's vision transformer, which basically a variant of a structure, like which is known as vision transformer VIT. Now, the structure is optimized, so let me write it, to process images in a way that is very efficient. It can learn faster, use less compute power, and things like that. So let me just uh, tell you about a mathematical intuition, that how I know how it works and things like that. So uh, let me just bring up my tab here. Cool. Now I hope the tab is here. Okay. Now if you look at the mathematically, we'll talk about a loss function. So the sigmoid loss, I'm going to talk about sigmoid loss here. So if you go here on this SigLIP, it says that it uses a sigmoid loss for language image pre-training, and it uses that, and you can find out the architecture here. So weight, shape optimized, and things like that. Right now, if you find out a sigmoid loss, it's a mathematical function. So if you're not aware, it's a mathematical function. If you would have, and this is very basic, you would have studied in deep learning or even prior to that, if you are familiar with logistic regression and things like that, you will understand these things. Now, it's a mathematical function that maps the value. Let me just write it here. That maps a value from a range between 0 and 1. And this is very fundamental. It basically helps your model transform the, or not model, helps you transform the output of a model into probabilities. So basically, it has a mechanism that basically transform the output, so it creates a probability, between 0 and 1. And what will happen if you don't use sigmoid laws in that case? If you don't use sigmoid laws and SigLIP, of course, while choosing a visual encoder, and I will show the inference of this model that I'm talking, why this is powerful. Having 3 billion parameters have already performed better than Llava 7B and the other multimodal models that we have on multiple benchmarks. It has outperformed the bigger multimodal LLMs like 7B variants, and that's why the way they have trained this is important. Now, if you use without SigLip, you might need a different loss function that might be compute intensive and also limits how much data that you have. So two things which goes in the favor of Sigmoid loss is that it less compute intensive, and I just said earlier it can work with less data. So if you want to fine tune or train, I will say, if you want to train a pre-trained multimodal base model or a language model, you can consider SigLip as a visual encoder. That is fantastic to use with. Now, I'm not go too much technical into the mathematics of it, but probably just for just for the sake of interest. Now imagine if you have an image vector. So let me just write it over here, and then we'll go into the inference and write some code. Now imagine if you have an image vector I, and then you have a text vector. So let me just write it over here. And if, oh, I have not been showing it here, excuse me, my bad. If you have a text vector called t, and before that I will just show you, this is what I have written. So two things, that's I'm talking about SigLip. You just sigmoid loss, it has an image text matching, better understanding with less data, and then architecture of it, sigmoid loss, like it uses a mathematical function, less compute intensive and less data. This is what we have written so far on the tab, and I will give the screen grab in the description. Now imagine if you have an image vector I and a text vector t, and so how the model compute a score. So if you, this is how model compute a score. So this is how model compute a score, like how well two matches are, or how well, not two matches, how well these two match. One is image vector and the other is a text vector. So this is how we call it. Now let's call this S of course, we're gonna write a function. So S of IT. This is how we mathematically write it. And then this score is then passed through a sigmoid function. So this is how we write a sigmoid function. This is how I'm gonna write S of IT, and then you write and say the formula is like 1 plus e to the power, uh, and this is how you define it. Very simple. And this can become a z also, so you can call it a j, so it become 1 by 1 plus e to the power minus g, so it can also become like that. Now if I and t are good match, so for example, if you call this thing, let me just make it a more simpler. If you call this thing j, so this entire formula become 1 plus 1 minus e to the power minus g, and now you have to calculate this g, of course, through different techniques. Now if this, if I and t are good matches, now if I and t match is good, if the match is good, Then you want s of I to, so this j to be high, so this has to be higher. Okay, so this will be high, and if high, and making the sigmoid output closer to 1, so this will be closer to 1, closer to 1, and if it's not a good match, then it will be closer to 0 or towards 0. It's low, and let me just do, this will be low, and I of t match is not good. Now this is how it works, and then you can calculate the loss. I'm not going too technical. Probably I have forgot myself the formula, but I have written a note here for that. Now for a given pair, the sigmoid loss, uh, like this, let's try it out. So I have a mathematical formula here, but I'll not be explaining much in detail. But this is how you can calculate the log function in this case. So you have s of it, and then this goes, and then you do 1 minus y, and then log of 1 minus, and again the formulas remain the s of it. So this is how you calculate the loss for one pair, and then you find out the, basically this is for penalty, you find out the incorrect predictions, and the model's objective is like during the training to minimize the loss. So if you have n number of batch size, the model learns for all the batches, try to minimize based on the loss function. So, and well, I already have explained that why loss function, because uh, it also helps you enable larger batch sizes. I've explained it from here, less compute intensive, less data, and things like that. So this is the overall realm behind this IMP version 1 3B model. Now let's try it out and see how we can inference this on a Google Colab, and see for a couple of examples. I'll tell you that where you can use this for some of the use cases. Now, the first thing that you have to do, of course, let me make it a bit bigger so you can see it. You can see I am on Colab. I'm gonna make it a bit bigger, 125 or things like that. You need a few things to install. So you do pip install thingy of the latest transformers. So I'm gonna do transformer thingy, and then I need EI knobs and things like that. So pip install. Uh, I need pillow for image. So pillow, and then I need accelerate, and then I need EI knobs. Now these are the things that I need for the installation. It will install, and once it install, you can just get it from uh, torch thingy. So let's do that. So I'm gonna do is from torch, or not torch, from transformer. So first we need import torch. Now let me just come a bit down. Import torch is there. Now I'm gonna do from transformers import. We need auto model for causal LM because we are going to do a generation thing, not a filling thing. So it's not a masks language thing. So it's a generation thing. So from transformers import auto model. Uh, for it's not showing me. Okay, you can see it's shown auto tokenizer, and then we need image from pillow. So from pil import I should be capital image thingy. We have to bind it to CUDA. So let's bind it to CUDA now. So what I'm going to do is torch dot set default. Show me now. Set default, not device, not tensor. Okay, so device to, and here I'm going to write CUDA. So let's do it CUDA here. Cool. And now I'm gonna do a model thingy. So let's do model equals, and this is the model we're gonna import or download from this repository. What I'm gonna do is from pre-read, you can see it shows me the Eleuther AI. Great. They are the creator of the open source community for AI, guys. Eleuther AI, the bloke on the hugging face, the Meta AI, Together AI, Together Computer, whatnot, right? All of these creators, credit goes to them. Huge kudos for what they do for the open source community. Now, here I'm gonna use auto model for causal LM, from pre-trained, but I'm going to change the uh, a few things here. The first thing that we're gonna change is, let me just do, we're gonna copy the model from here. So let's just come and copy this path and just pass this. This is now I'm gonna give my model name, I'm going to define a torch d type. So let's just do torch d type equals, and then you do torch dot float 16, and then you have low CPU memory use. I'm not going to use that. I'm going to do device map auto. So device, you can also do device map CUDA, you can do device map CPU, you can do device map auto. It depends on what kind of compute power you have and what how do you want to inference it. So auto is better in my case, so I'm going to do auto. If you do CUDA, it will automatically be using CUDA. If you do auto, it uploads some weights to the CPU depending on what kind of power you have in the system. Now trust remote code, yeah, let's do that. Trust remote code true. I don't need low CPU, so I'll just remove that. Now this is my model thingy. Once you have the model, same goes for tokenizer. Okay, so I'm gonna do tokenizer. So let's bring tokenizer here. So for this, let's copy this thing. So I'm gonna copy, and I also need a tokenizer from this only, and I'm gonna just do trust remote code true. So trust remote code true, and this gives us the model and the tokenizer. So let's do that. It's going to download some model. You can see it says, okay, you can see it's downloading. You have to do downloading SARs, 7 different types of weights it will download, and then you're gonna write a text. That how we're gonna do a text thingy, and you can find out that inference here. But I'm trying to look at, so let me just copy this. Okay, probably for you, but I'll show you a couple of use cases where you can use it. We'll try to test it out on few different types of images and see how good it is. Okay, so let's do that. Hmm. And prompt also plays a important role, guys. So this is something that we have to also see. Now you can see what are the colors of the bus in the image because it's giving you that, but I'm not gonna do that. I'm gonna say, let me just see. So let's change a bit of the prompt. So let's come here and I'll make this doc string. So let's do that. And yeah, so let's do a chat between yeah, this looks nice. Now I need an image. You can see the model has been downloaded, the tokenizer. So if you just want to print the model, let's do that. So I'm going to do model and see the pipeline of the model. And you can get the model and you can find out all the layers and high level layers and things like that, the entire pipeline. Now, here I need an image. You can upload it in the runtime. So let's upload that. I have a sample image I'm going to upload. So this is a skin related image. You can see I have a skin disease, common skin rashes. I'm trying to see if that model is able to derive some kind of inference for this is skin related images. So you can do some use cases in the field of medical images and healthcare and things like that. So you can see I have a sample JPG. So let's do that. So I'm gonna just do sample. Now it says a chat between a curious user and artificial intelligence assistant. That is fine. The assistant gives helpful, detailed, and polite answer to the user's question, which is also fine. I'm gonna say analyze the image. I'm not gonna ask this question. So let's ask analyze the image, and then I'm just running it. So once I run it, the next thing I'm gonna write is the to fetch the output. So for that, you're gonna do input IDs, and then you say tokenizer. So here in tokenizer, you do text, return tensor PyTorch, and then input IDs, and then after that you say image tensor. So image tensor equals, and then you say model dot image, and you do model dot image processor or image dot preprocess. Preprocess, correct. Image dot preprocess, and then you pass your image tensor. And now the next thing is to get the output IDs. So for that, let's get output IDs, and then you can pass a lot of things over here. So model.generate. So let's pass that function, and in model.generate, I'm going to pass my input IDs. So input underscore IDs, and then I'm going to input IDs, and then I'm going to pass max new tokens. So max new tokens and max new tokens. Let's keep it 300, not more than that. I just want to show you that if that works good for few use cases. Now max new tokens and then images equal. So images equal image underscore tensor. And then you write use cache, and then you do true, that if there's a value is already there, so use cache true. And then the first one, so this is okay, and let's print the tokenizer. So print tokenizer dot decode. We're gonna decode the output IDS. Now I'm gonna pass my output IDS and then pass the input IDS and the shape of that. So shape and input IDS, input IDS, and then you can also pass skip special tokens true. So let's do skip special tokens. It's a boolean value, so true, and then you just do strip. So strip. This is fantastic. Now let's run this and see if it gives any error or it works. So on you can see I'm running on a V100 GPU, which is on Google Colab Pro. It gives you an answer. Now let me just copy this. Uh, I'm just going to copy and paste it here. Let me just paste it here. This looks like a good answer. Now let me make it a bit bigger so you can read this, and I can just close this. It says the image features a closer view of a person's arm. So you can see this is the image that we have taken, showcasing a red rash or skin irritation. So it's able to find out a bit of, like it has a bit of findings from the images. It says the rash appears to be quite large. That is right, covers a significant portion of the arm. The person's arm is the main focus of the image, and the redness is clearly visible, indicating a possible skin condition, or irritation. This works fine for me, so that was working fine, and this is the image that we uploaded. Now let's try it out with some other images as well. If I have some image, you can see I have a perplexity image. So if you don't know what perplexity image I'm talking, perplexity provides you a free playground. You can play with a lot of LLMs here, like Mixtral ATX 7B and things like that, in completely in free. So if you ask what is AI, it will give you from Mixtral ATX 7B. So it's completely free. I have taken the screenshot of this, and what I want now is to generate a test case for me. So let's see if it's able to do that. So what I'm going to do is I'm going to make a few changes here in the, of course, the image name needs to be changed. So let's call it perplexity labs.png. And here a detailed and polite answer to analyze the image, not analyze the image, analyze the image and generate test cases for the software engineers, or for the software testers, and polite answers to the user questions. I will also change this. I'll say and generate. This assistant gives helpful, not gives. This assistant generates helpful and detailed test cases and edge cases for an application screenshot, something like this. Now imagine if you are working for a software development use case where you want to bring multimodal capabilities to generate test cases of your application screenshots or the architecture diagrams and things like that. How you can do that? So this is how you can do that. So let's try it out and see what it does. Now I give Perplexity Labs. I will increase the new tokens to 400 and see if it's able to generate something. And let's see that. And meanwhile, I'll just add a new cell to see what it gives. And again, you can play around with the prompt. You can design a good looking prompt for this IMP version 1.3b. So IMP version 1.3b, you can see it gives me a very good answer. It says the image displays a black screen with a message on it, which is fantastic. It's possibly from a computer program or a messaging app. That is what it is. As a software tester, you can create test cases to evaluate the software's response to various scenarios. It gives you some scenarios such that Verify that the software displays an appropriate message when it is unable to help. You can see it over here. It says, hello, how can I help you? Perplexity is already doing it. And you have test the software's ability to handle different types of request or input, such as invalid or unexpected data. You can put something which is not there, and so this kind of testing. So fantastic. I mean, I loved both the responses, and so far you have seen two use cases. One is the image of skin rashes, and this image is of test cases generation. Let me also try it out quickly with a Yahoo Finance image. I want to see if that it's able to get me and charts and things. So what I'm going to do is, let me take a screenshot of the selected area. I'm going to copy this part here, capture, download, and download. So let me just download this, and let me just call it MSFT. I'm going to call this MSFT. Come over here, upload the images, MSFT, and I'm just after MSFT. I'm gonna change this MSFT here. So let me just do that. So msft.png. Now I'm not going to call this as generating a test case and stuff. I'm gonna just call analyze the image. Helpful and detailed answer. The assistant gives because it uses phi2 as the text model, so it should have a bit of mathematical and analytical abilities. That's what phi2 says. Analyze the image, and let's ask this question. And let's see what it does. This is our final try because we already have tried for two use cases. One is for software development test cases generation, and the other one is a healthcare use case that we look. Now, if you look at here, it says the image displays a close-up of a computer screen showing the stock market data for Microsoft. Fantastic! It gets the Microsoft Corporation, guys, MSFT, from the text. The stock price is displayed prominently within the current price being. It gets the current price. Let's see that, which is 4057. Wow, fantastic. It gives you, but probably which one it takes. Let me see. Have it taken this one? Oh, it's getting changes. So I think the image that we uploaded was for that. Oh, fantastic. The stock price is displayed prominently with the current price being 40557. The screen also includes a summary of the stock performance. This is a fantastic use case to work on. You can just try to bring in these images, and you can just create a report out of it for the stock perform people who work in this trading and on things like that, which is fantastic. So you can see how capable is this. You are able to run this on a single consumer GPU. You can do it on T4 as well. I have tried it out. It works fine. You should go ahead and try that out as well. Now, let me know what are you doing with this multimodal or the small multimodal LLM, IMP version 1.3B, which is a fantastic small multimodal LLM to work with. But this ends our experimentation, guys, today with EMP version 1.3B. That ends our experimentation with Imp version 1.3B for this video, guys. And I hope now you understood that how SigLIP has contributed and where you can use this multimodal small language model. Now the code will be available on my GitHub repository. I will give the link in description, and we'll have more videos coming on from a RAG standpoint utilizing multimodal SLMs or multimodal LLMs. We'll see that in upcoming videos. If you have any thoughts, feedbacks, or questions, please let me know in the comment box. You can also reach out to me through my social media channels. Find those information on the channel banner and also the channels about us. If you haven't subscribed the channel yet, please do subscribe the channel. If you like the content, please hit the like icon and share the videos and the channel with your friends and to peer. Thank you so much for watching. See you in the next one.